Welcome to this topic on electrode potentials and electrochemical cells. We will explore how redox reactions can produce electricity and how we can predict the direction of these reactions. Focus and learning outcomes, redox reactions as the basis of electrochemistry, defining standard electrode potential, E degree. Understand standard electrode potential, E degree, how it is measured relative to the standard hydrogen electrode, SHE, and how these values are used to predict the direction and feasibility of redox reactions. Use of standard electrode potential data to calculate the electromotive force, EMF, of an electrochemical cell. Oxidation is defined as the loss of electrons, while reduction is the gain of electrons, commonly remembered using the mnemonic oil rig. In any redox reaction, oxidation and reduction always occur together because electrons lost by one species must be gained by another. In electrochemical cells, these processes are physically separated into two half cells, which allows electrical energy to be produced or measured. The standard electrode potential, symbol E degree, is a measure of the tendency of a species to be reduced, meaning to gain electrons. Importantly, it is always defined as a reduction potential, even if the species is more likely to be oxidized in practice. Because it is impossible to measure the absolute potential of a single half cell, electrode potentials are measured relative to a reference half cell, the standard hydrogen electrode. An E degree value therefore indicates how readily a half cell undergoes reduction compared with hydrogen. A more positive E degree value means a greater tendency to gain electrons and be reduced, while a more negative value indicates a lower tendency to be reduced and a greater tendency to be oxidized. Structure and purpose of the standard hydrogen electrode, standard conditions for electrode potentials, how standard electrode potentials are measured. The standard hydrogen electrode, SHE, is the universal reference point against which all standard electrode potentials are measured. By definition, it has an electrode potential of exactly 0.00 V under standard conditions. The SHE consists of a platinum electrode coated in finely divided platinum, which acts as a catalyst, immersed in a solution containing hydrogen ions at a concentration of 1 mol dm cubed. Hydrogen gas at a pressure of 100 kilopascals is bubbled over the platinum surface. Platinum is used because it is inert and provides a surface for electron transfer without taking part in the reaction. Standard electrode potentials are only valid under standard conditions. These conditions are a temperature of 298 K, 25 degrees Celsius, a pressure of 100 kilopascals for any gases involved, and solution concentrations of 1 mol dm cubed for aqueous species. These conditions ensure consistency and allow fair comparison between different half cells. If conditions deviate from standard, electrode potentials will change. To measure the standard electrode potential of a half cell, it is connected to the standard hydrogen electrode under standard conditions. The two half cells are joined by a salt bridge, which allows ions to move and maintain electrical neutrality, and a high-resistance voltmeter, which measures the potential difference without allowing significant current to flow. The voltmeter reading gives the magnitude of the potential difference, while the direction of electron flow indicates which half cell is acting as the anode and which as the cathode. If electrons flow from the test half cell to the SHE, the test half cell has a negative E degree value. If electrons flow from the SHE to the test half cell, the test half cell has a positive E degree value. Structure of an electrochemical cell, calculating the electromotive force, EMF, predicting feasibility of redox reactions. An electrochemical cell consists of two half cells connected by an external circuit and a salt bridge. Each half cell contains an electrode in contact with a solution of its ions. In this cell, zinc acts as the anode where oxidation occurs, and copper is the cathode where reduction occurs. Electrons flow through the external circuit from zinc to copper, producing an electric current. The salt bridge, often containing potassium nitrate, allows ions to move to balance charge and complete the circuit. The electromotive force, or EMF, of an electrochemical cell is the overall potential difference between the two half cells under standard conditions. It is calculated using the equation E degree cell equals E degree, positive electrode, E degree, negative electrode. The positive electrode is the half cell with the more positive standard electrode potential. Standard electrode potentials allow chemists to predict whether a redox reaction is feasible. If the calculated E degree cell value is positive, the reaction is thermodynamically feasible under standard conditions. If it is negative, the reaction is not feasible in that direction. This principle can also be applied without full calculations by comparing E degree values directly. The half cell with the more negative E degree value will be oxidized, while the half cell with the more positive E degree value will be reduced. Understanding the electrochemical series, worked example using electrode potentials, applications, batteries and corrosion. The electrochemical series is a list of standard electrode potentials arranged from most negative to most positive. It provides a powerful summary of redox behavior. Species at the top of the series, with very negative E degree values, are strong reducing agents because they readily lose electrons. Species at the bottom, with very positive E degree values, are strong oxidizing agents because they readily gain electrons. Consider a cell made from silver and copper half cells. The E degree value for AgAg is plus 0.80 V, while the E degree value for Cu2Cu is plus 0.34 V. Silver therefore acts as the cathode and copper as the anode. Using the EMF equation, E degree cell equals 0.80, 0.34 is equal to plus 0.46 V. This positive value shows that the reaction is feasible. In an exam answer, students should also state that copper is oxidized and silver ions are reduced, supporting this with half equations if required. Electrode potentials have important real-world applications, particularly in batteries and corrosion prevention. In batteries, chemical energy from redox reactions is converted into electrical energy, with carefully chosen half cells providing a useful EMF. Rechargeable batteries rely on reversible redox reactions. Electrode potentials also explain why certain metals corrode more easily than others. Metals with more negative E degree values, such as iron, are more readily oxidized and therefore more prone to corrosion. Sacrificial protection uses this principle by attaching a more reactive metal, such as zinc, to iron structures so that the zinc oxidizes instead. Hydrogen fuel cells and electrode potentials, practical skills and experimental understanding, exam technique and key takeaways. In a hydrogen fuel cell, hydrogen is oxidized at the anode and oxygen is reduced at the cathode, producing water as the only chemical product. Electrode potentials can be used to calculate the EMF of the cell and explain why the reaction is feasible. Fuel cells are attractive as energy sources because they are efficient and produce no carbon dioxide at the point of use. However, challenges include hydrogen storage and production. Although it is not required to carry out full electrode potential experiments, strong practical understanding is expected, which includes recognizing cell notation, identifying half cells, understanding the purpose of the salt bridge, and interpreting voltmeter readings. Electrode potentials allow us to compare redox reactions and predict electrochemical cell behavior. Understanding electron transfer is key to understanding how cells produce electricity. Thank you for watching.